Hello friends, this is Infinity Vision and this is the section NCERT solutions of 12th class. So today we'll be discussing relations and functions miscellaneous exercise, which is the exercise 1.5. Now it consists of all the questions from all the exercises from all the topics which we have covered so far, okay? But these questions are a bit difficult, you can say, a little bit difficult. They need some trick, and we'll see all the questions one by one. So let's start with the first question. So the first question is, let f from R to R be defined as fx is equal to 10x plus 7. Then the function g defined from R to R such that g of f is equal to f of g is equal to, this is I, is equal to I of R. So now what we have to find here, so first let's see very carefully. We have to find such a function g such that g of f is equal to identity function. So what we need to find is g is actually the inverse of f. So this is what he needs to tell you from this statement, okay, that g is the inverse of f. So to find the inverse of f, first of all we have to check whether the function is 1, 1 and onto. So if we have fx is equal to fy, we get 10x plus 7 is equal to 10y plus 7. If you solve it, you get x is equal to y, right? So therefore this function is 1, 1. Similarly, onto, it will be onto, since it's a linear function, right? Defined from R to R, it will be onto for sure. So these two properties, if we have checked, then we can ensure that this function is invertible. So if this function is invertible, we'll simply find the inverse here. So y is equal to 10x plus 7. Find the value of x from here. 10x is equal to y minus 7 upon, x is equal to y minus 7 upon 10. So this will be the inverse function of fx. Now you can simply prove that now we have g of x is equal to x minus 7 upon 10. And we know that f of x is equal to 10x plus 7. Now from both these, just simply show that f of g is equal to g of f, okay? So if you put f of g, you will get the value x. If you put g of f, you will get the value x. So it's very easy to solve. So this was just 3-line question, right? But we still have to prove that the function is 1, 1 and onto in order to find the inverse. Let's see the next question now. So this function f is defined from w to w, where w is the set of all the whole numbers. So this is defined as fn is equal to n minus 1 when n is odd, and fn is equal to n plus 1 when n is even. Show that f is invertible. So if we need to show that it is invertible, we have to prove that it's a 1, 1 function as well as onto function, okay? So let's take two values. fm is equal to m minus 1 and fn is equal to n plus 1, okay? So here we are taking m is odd and n is even. So let's take a case where f of m is equal to f of n. Now what we need to find out, that m should be equal to n. Only in that case this will be a invertible function, right? So if you see here, you get m minus 1 is equal to n plus 1. m minus n is equal to 2. So just take a few minutes and think why this cannot be true. Okay, I'll give you a hint. M is odd, N is even, and M minus N is 2. Is this possible? So just think it over. Is it possible to have such a statement? Now, M minus N is equal to 2. This is not possible because M is odd and N is even. Let's suppose you have an odd number 5 and an even number 2. If you subtract these two, you will get an odd number. Okay, so the difference of an odd and an even number cannot be an even number. So this possibility is not true. Okay, so M odd and N even, this is not possible. So let's take some other cases, like if M is even and N is even. So if both of them are even, then f of M is equal to f of N, means M plus 1 is equal to N plus 1, means M is equal to N. Okay, so if both are even or if both are odd, in both the cases M will be equal to N. So this function will become 1 function, right? Now the case which we took previously, where one was odd and the other one was even, that case has to be ignored, right? Because that is not possible. We just have to see this case. So this will be invertible only if it is 1 and onto as well. So how do you prove that this is an onto function? By taking some examples. Let's suppose N is 1. Okay, what is the value of f of 1? This is equal to 0. If N is 2, what is f of 2? This is equal to 3. Okay, so is it covering all the values that you have to see? Okay, so simply start putting all the values and you'll simply see that it's covering all the values starting from 0 to all the whole numbers. So therefore it will be onto as well. Now you have to find the inverse of this function. So actually the inverse of this function will be this function itself. Okay, so you can easily check inverse function gx or gn is equal to same as this, n minus 1 if n is odd and n plus 1 when n is even. So it's exactly the same function as fn. Okay, so you don't need to worry about that. So you can simply check and simply verify if this is true or not. You can check f of g of n. Okay, so first case, if n is odd. If n is odd, what is g of n? N minus 1. Now if n was odd, n minus 1 will be even. So the formula will be n plus 1. So this becomes n minus 1 plus 1 is equal to n. So if you check all the cases, right? If you take f of g of n and simply check f of g of n when n is even, this will also be equal to n. And similarly for g of f of n when n is odd, similarly for g of f of n when n is even, it will all come out to be equal to n. So no need to worry about that. So let's move on now to the next question. Now this, you have to make a little correction over here. This is actually square. This is x square minus 3x plus 2. So this function f is defined from R to R as x square minus 3x plus 2. We have to find f of x. Okay, so what is f of x? This is equal to, let's switch to the white one, x square minus 3x plus 2. Okay, so what is f of x? So in place of x you will put this value, x square minus 3x plus 2 whole square minus 3 times x square minus 3x plus 2 plus 2. So simply expand this and solve this. So let's solve it. X to the power 4 plus 9x square plus 4 minus 6x cube minus 12x plus 4x square minus 3x square plus 9x minus 6 plus 2. So here we wrote all the terms, right? So 4 minus 6 plus 2, it all cancels out, right? So we are left with x to the power 4. I've written this term. What is the term of x cube? Just 6x cube. I've written this. X square plus 4x square. It's 9x square plus 4x square is 13x square. Minus 3x square gives you 10x square. I've written these. And minus 12x plus 9x. This gives you minus 3x. So this will be the answer. So let's move on to the next question now. The fourth one. The fourth question is, show that the function f defined from R to x belongs to R minus 1 to 1. So x lies between minus 1 to 1. Is defined by fx is equal to x upon 1 plus mod x. Show that this function is 1, 1 and on 2. Okay. So we'll take two cases. First, we have to check for 1, 1 function, and then we have to check for onto function. So simply for 1, 1 function, I'll take two values m and n and take fm is equal to fn. But this will be done for 4 different cases. Okay. So in first case, m is greater than 0, n is less than 0. So this will be the first case. So from here you get m upon 1 plus m is equal to n upon 1 minus n. Right? Since if n is less than 0, what will be mod n? This will be equal to minus n. Right? So if you cross multiply this, you get m minus mn is equal to m plus mn. Right? You get, so this will be n. M minus mn is equal to n plus mn. So you get m minus n is equal to m times n. Now m is greater than 0 and n is less than 0. So this thing is positive. One is positive, one is negative. This thing is negative. So this is not possible. Similarly, m less than 0, n greater than 0, not possible. So now we are left with only two cases, m greater than 0, n greater than 0. So in that case you get m upon 1 plus m, n upon 1 plus n. So you get mn plus n is equal to mn plus m. Right? So if you simply cancel this, you get m is equal to n. Okay? So just cross multiply and you will get m is equal to n. Similarly for m less than 0 and n less than 0, you get m is equal to n. So since for fm is equal to fn, m is equal to n, therefore this is a 1, 1 function for sure. So we need not worry about these two, okay? Since they were not equal in the first place. So we are checking their value, we are actually equating their value, they will never come out to be equal, and this case is not possible at all. Okay, this is not feasible, right? So therefore these two cases are not feasible, only two feasible cases are these two, and it is 1, 1 function for both the cases, right? So now let's check the condition for onto function. Now, what will be the inverse of this function? So this is actually y is equal to x upon 1 plus mod x. So we have to actually check the inverse of this function. So there will be two cases in this as well. So the two cases will be if y is negative and if y is positive, right? So if you actually cross multiply this, you get y plus mod x y is equal to x, right? So from here you get mod x y minus x is equal to minus y, right? So there will be two cases here. In first case x will be negative, in the second case x will be positive, and the values of x you will get will be, first case will be when y is negative. In that case x will be equal to y upon 1 plus y, and if y is positive it will be equal to y upon 1 minus y, right? So these are the two values which you will get. Now simply what you have to put, you have to put these values back here and you have to check whether you are getting f of g of x is equal to x. So if you get an x, that will be equal to an onto function. Okay. So now let's see the next question. Show that the function f defined from R to R given by fx is equal to x cube is injective. So injective means 1, 1. So if you have to prove that this is injective, assume fx is equal to fy. So you get x cube is equal to y cube. Okay. So this is only possible if x is equal to y. So therefore from fx is equal to fy we concluded that x is equal to y. Therefore this function is injective. Let's see the next one. Give example of two functions f defined from n to z and the other function g defined from z to z such that g of f is injective but g is not injective. So in this we'll take two examples. First we'll take fx is equal to x, right? And second we'll take gx is equal to mod x. Now tell me, is g injective? No. G is not injective. Why so? Since g of 1 is equal to g of minus 1. Okay? So this is not injective. But if we see g of f, so what is g of f of x? This is g of fx. What is fx? X. So this becomes g of x. But in this case there's one difference. Okay, this function g of fx, this is defined from n to z, right? But this function gx, this is defined from z to z. Now in this case, if this is only positive numbers here, only positive natural numbers here, right, then this function will definitely be 1, 1. Since if in that case you see g of 1 cannot be equal to any other value possible. So it was only equal to minus 1, but the negative values are excluded from here. Therefore, this function becomes injective. And it is only happening because of this difference, that g of fx is defined from n to z and gx is defined from z to z, right? Let's see the next question now. Give examples of two functions f n to n and g n to n such that g of f is onto but f is not onto. So in this case, we'll take two examples. Let's say the first example, fx is equal to x plus 1, right? And let's see the second example, gx is equal to x minus 1 when x is greater than equal to 2 and 1 when x is equal to 1. Okay, so these are two functions. In this case, we have to show that g of f is onto but f is not onto, right? What is fx? This is x plus 1. Okay, so can fx ever be equal to 1? Now this fx has n in the codomain. Okay, so all the numbers are coming including 1, but for this to be 1, x should be equal to 0. So x is equal to 0, this is not possible since this function is defined from n to n. Therefore, f is not onto. Now let's see g of f of x. So what is g of f of x? This is g of x plus 1, right? Now there will be two values of this, right? What if x is equal to 1? Then what will be the value? That will be g of 2, that will come under this, right? But what will be happening if x is equal to 0? Now see, you cannot put x is equal to 0 here since fx is there, right? X is equal to 0 is not possible. Therefore, you will get only one case in which you get x plus 1 minus 1. Since x plus 1 will be greater than equal to 2. So from here you get this is equal to x, right? Therefore, g of fx will be onto. Right? Simple. Since g of f of x is equal to x, therefore this is an identity function, right? G of f of x is equal to x. If you put 1, you will get 1. If you put 2, you will get 2. In every case, this will be an onto function. So therefore, in this case, f is not onto, but g of f of x is onto. Right? Moving on to the next question. Let a non-empty set P x consider Px, which is the set of all the subsets of x. Define a relation R in Px as follows. For subsets AB in Px, A are B if and only if A subset of B. Is R an equivalence relation on Px? Justify your answer. For equivalence relation, first we'll have to check the reflexive property. So first you have to check ARA. Is ARA true? Yes, this is true, since A is a subset of A. Right? Every set is a subset of itself. Now we'll have to check for symmetric. If A are B, then is BRA possible? See, if A are B, then A is a subset of B. Then B cannot be a subset of A. Right? So therefore this function is not symmetric. Last, we'll check for transitive. if A are B and B are C, right? So if A is a subset of B and B is a subset of C, then obviously A is a subset of C. So it will be reflexive and transitive but not symmetric. Therefore this is not an equivalence relation. Moving on, let's see the next question. Next question is from binary. Given a non-empty set X, consider the binary operation star px into px to px. Okay, so this binary operation is defined from px cross px to px, right? So now what you have to do is show that X is an identity element for this operation and X is the only invertible element in px with respect to operation star. Okay, so first let's see. So for invertible, what we have to show is, for identity element, what we have to show is A star X should be equal to A should be equal to X star A. So what is A star X? This is actually A intersection X. Okay, so what is A intersection S? This is X, the whole set. Okay, this is a non-empty set, and A is some set inside of X. What is A intersection X? So in this case, the intersection of these two will be A, right? So this is equal to A. Similarly, this is equal to X intersection A. Okay, so therefore X is an identity element for this operation. Now secondly, we have to show that X is the only invertible element in Px with respect to operation star. Okay, so A star B should be equal to X equal to B star A. So this we have to show that X is the only invertible element. Okay, so if for this case, okay, when is this true? When is A intersection B is equal to B intersection A is equal to X. Now the intersection of two sets means common area of two sets. The common area of two sets is the whole set X. So this is only possible if A is equal to B is equal to X. So therefore X is the only invertible element in Px with respect to operation star. Okay, so X is the identity element as well as the only invertible element. So let's move on to the next question. Find the number of all onto functions from 1, 2, 3 up to n. So what you have to do is actually, this is 1, 2, 3, 4 up to n, and this is 1, 2, 3, 4 up to n. So you have to find all the number of onto functions. For this to be an onto functions, there needs to be no element left in this set, right? So all the elements here should have a pre-image, right? So therefore all of these elements will be consumed. Now what you have to do is you have to actually link all the elements to some elements over here. So in how many ways can the first element be linked? So the first element can be linked in n ways. In how many ways the second element can be linked? Now 1 will be linked to some of the element. It can be linked with n minus 1 ways multiplied by n minus 2. There will be only one possibility left for the last one. So the answer will come out to be n factorial. Right? So this will be product of all the numbers starting from 1 to n. That is number of all the onto functions from set to itself. Let's see the next question now. Let S be a set ABC and T be a set 1, 2, 3. Find f inverse of the following functions f from S to T. Okay, so in this case, if you need to find f inverse, it will simply be 3a, 2b, and 1c. Okay, but in this case, f inverse is not possible since this function is not 1, 1 function. You can easily see from here, two elements b and c have the same image. Okay, f of b is equal to f of c. Therefore, this is not 1, 1 function. F inverse does not exist. Right? So, let's move on to the next one. Consider the binary operation star from R cross R to R and the binary operation O defined as A star B is A minus B and A OB is equal to A. Show that star is commutative but not associative. Okay, so let's start with star. Okay, so for star to be commutative, A star B and B star A should be equal. So let's see, what is A star B? A minus B mod. What is B star A? B minus A mod. So this is actually minus of A minus B mod, right? This minus sign can be cancelled by mod. So this is also equal to A minus B mod. So therefore A star B is equal to B star A. Therefore this operation is commutative. Now let's check for the associative property. Okay, so let's first check A star B star C, and this should not be equal to A star B star C, right? I'll take few examples. 1 star 2 star 3. What is this? What is 1 star 2? This is mod of 1 minus 2 star 3. This is 1 star 3. This is mod of 1 minus 3 is equal to 2. What is this value? 1 star 2 star 3. What is 2 star 3? This is mod of 2 minus 3. What is mod of 2 minus 3? 1. What is 1 star 1? 0. So therefore, this is not associative. Right? So we have shown that this star is commutative but not associative. Now we have to show that O is associative but not commutative. So we can simply show that as well. Let's start with the operation O. What is AOB? This will be equal to A. Since AOB is A, if you have A and B two numbers, okay, then you just pick the first one and that will be the operation. What will be BOA? This will be equal to B. So AOB is not equal to BOA. Therefore, this is not commutative. Right? Now we have to check the associative property. AOB OC, right? And here we have AO BOC. What is AOB? A. What is AOC? A. What is BOC? B. What is AOB? A. So these two are equal. Therefore, this is associative. But this is not commutative, right? Further show that A star BOC is equal to A star BO A star C. Okay. So this is what we have to prove next. A star BOC is equal to A star BO A star C. So what is A star BOC? Okay, so this is A star. What is BOC? B. What is A star B? Mod of A minus B. And here we have A star B O A star C. So if we take O of two numbers, we just pick the first one and neglect the second one. This was A or B, so therefore this becomes A star B. And what is A star B? Mod of A minus B. So therefore this condition is true. If it is so, we say that this operation star distributes over the operation O. So does O distribute over R star? So you can simply show that as well. You have to replace this star with O and O with star. Okay. So we can also show that. Let's see that. So we have to show AO B star C is equal to AOB star AOC. Okay. What is AO B star C? So you don't need to write B star C. This will be actually equal to mod B minus C. But since you are just taking O operation here, this will simply become A. What is AOB? A. What is AOC? A. What is A star A? Mod A minus A. 0. But in this side we are getting A. So therefore this O does not distribute over star. But the reverse is true. Okay. So let's see the next question now. Given a non-empty set star, let star be Px to Px to Px be defined as A star B is A minus B union B minus A. Show that the empty set phi is the identity for the operation star and all the elements of A of Px are invertible with A inverse is equal to A. Okay. So let's see how phi is the identity element. So if we take A star phi, this should be equal to A is equal to phi star A. So what is A star phi? This is A minus phi union phi minus A. What is this? Phi minus A union A minus phi. So what is A minus phi? A union phi. Phi union A. So in both the cases you are getting A. So therefore empty set phi is the identity for this operation. And next we have to show that all the elements of Px are invertible with A inverse is equal to A. So how will we prove that? Let's see. So if you take A star B, and what do we have to show when we have to show that it is an inverse? So what will you do? So you will simply take A star B is equal to B star A. Just think it through. What will this be equal to? It should be equal to what? So if A star B and B star A both should be equal for this to be invertible, and this should be equal to phi. Now is this possible? Now this is possible since phi is the identity element in this case. Okay, so if you actually take A star A, what will you get? Let's see. You get A minus A union A minus A. Now what is this equal to? Is this equal to phi? Yes. Since what is A minus A? If you subtract A from A, this is equal to phi. Similarly, this is equal to phi. So therefore, this answer is equal to 5. So therefore, the inverse of A will be equal to A itself. So this was a bit typical question. Okay. So let's move on to the next one now. Define a binary operation star on the set 0 to 5 as A star B is A plus B if A plus B is less than 6 and A plus B plus 6 minus 6 if A plus B is greater than or equal to 6. Show that 0 is the identity element for this operation and each element A is not equal to 0 of the set is invertible with 6 minus A being inverse. So we have to show that 0 is the identity element here. So what we have to show that A star 0 is equal to A is equal to 0 star A. Now since we are taking A star 0, A belongs to this set 0 to 5. A plus 0 will always be less than 6. So therefore this simply becomes A plus 0 and this becomes 0 plus A, which is true. So therefore 0 is the identity element for this operation. Now let's see the case of inverse. If you have A plus B, okay, and in that case that should actually come as the inverse. So how will you solve that in case of inverse? So you will have two cases. A plus B should be equal to 0 and this should be equal to B plus A if A plus B is less than 6. So this is the first case. And second case is if A plus B is greater than or equal to 6, then A plus B minus 6 should be equal to 0 is equal to B plus A minus 6. So what do we get from the first equation? B is equal to minus A. What do we get from the second equation? B is equal to 6 minus A. So is this possible B is equal to minus A? No, this is not possible since the set is only from 0 to 5. No negative numbers are allowed. So the inverse will be equal to B is equal to 6 minus A. Right? So that's how we solve the questions of binary operations which include identities as well as the inverse. Let's see the next question now. So A is defined from minus 1, 0, 1, 2 and B is this, and F, G are two functions defined by Fx is equal to x square minus x and Gx is equal to 2 times x minus half mod minus 1. So we have to check if Fx and Gx are equal. So first let's check F of minus 1. So this is equal to minus 1 square minus 1. This is equal to 0. What is G of minus 1? So this is equal to 2 times minus 1 minus half minus 1. Right? In this question, it is written that let A is a set minus 1, 0, 1 and 2 and B is this set minus 4, minus 2, 0 and 2. And F and G are two functions defined from A to B such that Fx is x square minus x and Gx is this. We have to see whether F and G are equal or not. So first we'll check with F of minus 1. This is minus 1 square minus minus 1. So 1 plus 1 is 2. What is G of minus 1? 2 times minus 1 minus 1 by 2 minus 1. So 3 minus 1, this is 2. So F of minus 1 and G of minus 1, these both are equal. Right? So this is the first condition you're getting. Now let's check for F of 0 and G of 0. So what is F of 0? This is 0 square minus 0, 0. What is G of 0? This is 2 times 0 minus half minus 1. So this is 1 minus 1 is 0. So therefore f of 0 is equal to g of 0. So we are only left with 1 and 2. Let's check for them as well. So what is f of 1? 1 square minus 1. This is 0. What is g of 1? 2 times 1 minus half minus 1. So 2 times half minus 1, 0. Now let's check for 2. What is f of 2? 2 square minus 2 is equal to 2. What is g of 2? 2 times 2 minus half minus 1, 3 minus 1, 2. So therefore f of 1 is equal to g of 1, f of 2 is equal to g of 2. All the values are equal, therefore f and g are both equal functions. Let's move on to the next question now. Let A be 1, 2, 3, this said, the number of relations containing 1, 2, 1, 3, which are reflexive and symmetric but not transitive. So see this question very carefully. We have to see the number of relations which are symmetric and reflexive but not transitive. So if we take 1, 2, 1, 3, if the relation is symmetric, then 3, 1 will also be there. Similarly, 2, 1 will also be there, right? And for it to be reflexive, 1, 1, 2, 2, 3, 3 should be there. So therefore, this is the only possible relation containing 1, 2 and 1, 3, which is reflexive and symmetric but not transitive, okay? So even if we add 2, 3 or 3, 2 here, right, then it will be chaos. Then it will become transitive, okay? Since if you add 2, 3, you will have to add 3, 2. If you add both of them, then it will become transitive. So the number is only 1. Let's see the next one. It's pretty similar one. Let A be said from 1 to 3, find the number of equivalence relation containing 1, 2. Okay, so first you have to add 1, 1, 2, 2, 3, 3, since these are necessary for reflexive property. If you have 1, 2, you have to add 2, 1. Okay, and this will be an equivalence relation in itself. You can simply see this function is reflexive, this function is symmetric, and this function is transitive in every way, right? Now, what will be the second case? What can we add here? So what actually we can add here is, let's add 2, 3. So if you add 2, 3, you will have to add 3, 2, right? This is necessary. Now if you have 2, 3 and 1, 2, you have 1, 2 and 2, 3, you will have to add 1, 3 as well. And if you add 3, 1, 3, you will have to add 3, 1 as well. So this is the first equivalence relation you can get, and this is the second equivalence relation you can get. So the number of equivalence relation here will be 2. Let's see the next question. F defined from R to RB, signum function defined like this, and GB is the greatest integer function defined by Gx as box x, where this box x is greatest integer less than or equal to x. Does fog and Goff coincide in 0 to 1? So first let's check f of g of x. So if x lies between 0 to 1, okay, 0 to 1, there will be two cases. The first case will be x lies between 0 and 1, and the other case is x is equal to 1. So if x lies between 0 to 1, what will be the value of gx? So gx is greatest integer function of this. So therefore, gx will be equal to 0. And what will be f of 0? This will be equal to 0. Right? Now for x is equal to 1. If x is equal to 1, what is g of 1? This will be equal to 1. So we get f of 1. This is equal to 1. For x greater than 0, this is equal to 1. So this is the definition of f of g of x. Now let's check the definition of g of f of x. So if x lies between 0 to 1, it means x is greater than 0. Therefore, the value of fx should be equal to 1. What is g of 1? This will be equal to 1, right? Now, g of fx is this. F of gx has two conditions. Therefore, these two are not equal. They do not coincide. Let's see the next problem now. Number of binary operations on the set A, B. Now see, we have to tell how many binary operations are possible in this case. Okay, so we have 4 possibilities here, A for AB and AB, right? And 2 possibilities here, right? From here you will get 4 ordered pairs, AA, AB, BA and BB, and these are all getting linked with AB, right? So these are 4 sets and these are 2 elements. So the answer here will be equal to 2 to the power 4. So this is the formula which you have to remember. Okay, so if this binary operations we are checking between these, okay, these are 4 different ordered pairs which we are getting. So the total number of binary operations will be equal to 2 to the power 4, since the ordered pairs are actually in the form of 2 elements. So this was the last question, and this concludes our final exercise, which was the miscellaneous exercise for relation and function. Stay tuned for more chapters and more videos from us. This is Infinity Vision, and thank you.